Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 58. Mathematical Coherence, Derivative Closure, Jet Structure, and Consistency. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. In this part of our journey, we move deeper into Book 12, the phase of expert scrutiny and legitimacy. We have already seen that the holophase behaves like a true language, with an alphabet of derivative operators, a grammar of constraint chains, and a rich tridimensional semantics. We have compared it with the genetic code and understood why the holophase is not just a code, but a universal language in which all codes are embedded. Now we must go one level deeper. It is not enough for the picture to be beautiful or intuitively satisfying. For a framework that claims to speak about all of reality, we must ask a harder question. Is it mathematically coherent? Does the image of an infinite derivative tree really match a precise mathematical structure? Does everything fit together without contradiction? In this part, we answer that question. We show that the holophase is rooted in a well-defined mathematical backbone. We focus on three pillars that hold the structure together. The first pillar is derivative closure, the idea that taking more derivatives never forces us to leave the language. The second pillar is jet structure, the idea that there is a clear way to collect all the derivatives at a point into a complete local dictionary. The third pillar is consistency, the idea that all those derivatives must fit together in a way that tells one story rather than many conflicting ones. Together, these three ideas give the holophase a solid mathematical skeleton beneath its poetic skin. Let us begin with derivative closure. At the heart of the holophase is a very simple claim. Everything we ever need to say about the physical world can be written in terms of phi and its derivatives. Time, space, and motion are all expressions of how phi changes. New layers of behavior appear when we look at higher derivatives, but we never introduce a second fundamental field underneath phi. The universe is not built from phi on some days and something else on other days. It is always phi, changing in more and more structured ways. Derivative closure is the formal version of this claim. It means that when we take derivatives of phi, and then derivatives of those derivatives, and so on, we never escape the language we started with. We never have to say, now we need a completely new kind of entity which is not related to phi by any derivative at all. Instead, the whole hierarchy is built by repeating the same simple operation, asking again and again, how is this changing? You can picture this through a very simple analogy. Imagine you have a melody in music. The melody is like phi itself, the raw pattern. Now you ask, how fast is the pitch rising or falling? That is like a first derivative. You can ask again, how fast is that change itself changing? And you get something like musical acceleration or curvature. You can keep doing this, analyzing the melody in more and more detail, but you never leave the world of that melody. You are always talking about the same underlying line of notes, just at higher and higher levels of description. Mathematically, closure is guaranteed whenever phi is a smooth field, meaning that you are allowed to differentiate it as many times as you like. Every time you differentiate, you get another field, and that new field can be differentiated again. This property means that the holophase language is self-contained. The alphabet, which consists of ways of taking derivatives, is fixed once and for all. The vocabulary, which is the list of all possible derivative values, is infinite, but it is generated entirely from that same alphabet. There is no need to introduce new fundamental substances as you climb the tree. You just keep reading deeper into the same script. The second pillar is jet structure. Closure tells us that the tree of derivatives can, in principle, go on forever. Jet structure tells us how to organize that infinite tree at each single point in spacetime so that it becomes usable. Imagine you freeze the universe at one specific place and one specific moment. You ask, what is phi here? What are its slopes in time and space? What is its curvature? How are those curvatures themselves changing? If you keep asking these questions, you build an infinite list of numbers and tensors. That infinite list, sitting at that point, is what mathematicians call the jet of the field at that point. You can think of the jet as the complete local personality of phi. The value of phi tells you how high the field is at that point, like the height of a hill. The first derivatives tell you in which directions it is rising or falling. The second derivatives tell you whether you are standing in a valley, on a ridge, or on a flat saddle. The third derivatives tell you how sharply the shape is changing as you move. The higher derivatives continue this process, refining the description endlessly. In principle, if you knew the entire jet at a point, and if you assume the field is smooth, you could reconstruct how phi behaves in a small region around that point. The jet is the complete local dictionary of the field's behavior. In the Holophase language, the jet at a point contains all possible temporal, spatial, and motion echoes that can arise there. The temporal part of the jet tells you how phi is oscillating or drifting in time. The spatial part tells you how phi is structured and curved in space. The mixed and motion-related parts tell you how these patterns are being carried along or transported. When we speak about the master tree of derivatives, we are really speaking about the space of all possible jets, stitched together point by point across spacetime. The third pillar is consistency. Closure and jet structure give us an enormous amount of freedom. In principle, you could write down any numbers you like for all the derivatives at a point and call that a jet. But not every random list of numbers can really come from a smooth field. To be legitimate, the jet must satisfy certain mathematical relationships. These relationships are like the basic grammar rules of the language. They prevent contradictions and ensure that the story phi is telling is internally coherent. One of the simplest of these rules is the symmetry of mixed derivatives. In everyday language, it means that if you first look at how something changes in time, and then look at how that time change varies in space, you should get the same result as if you first look at how it changes in space, and then see how that spatial variation evolves in time. The order of questioning does not change the answer, as long as the field is smooth. In mathematics, this is known as the equality of mixed partial derivatives. It is a basic integrability condition, one of the ways we ensure that all the directional slopes and curvatures fit together into a single underlying surface. There are deeper consistency conditions as well. If you are given a map of slopes everywhere, and you are told that these slopes come from a single height function, then those slopes must satisfy the condition that going around a tiny closed loop brings you back to the same height. You cannot keep walking around in a circle and find that you are always going uphill. That would mean there is no true height function beneath the slopes. In the same way, the derivatives of phi must be compatible with the existence of phi itself. These requirements are expressed in conditions like the curl of a gradient being zero, or in more advanced forms like the Bianchi identities in general relativity. They are all statements that the many pieces of the jet must join to form one global story. On top of these basic symmetries, we place the physical laws themselves, which we have called constraint chains. These are more specific consistency rules that nature seems to enforce. Maxwell's equations for electromagnetism, the Schrödinger equation for quantum systems, the Navier-Stokes equations for fluids, and Einstein's field equations for gravity are all examples. Each of these is a statement that the derivatives of a particular phi field cannot vary freely. They must cooperate in very precise ways. They are grammar rules that say, if the jet looks like this here, then a moment later and a small distance away, the jet must look like that. Only those jets that satisfy all these constraints correspond to physically allowed states. When we put these three pillars together, we realize that the master tree is not just a poetic image, but a representation of a very concrete mathematical object, known as the jet bundle. To picture this, imagine that every point in spacetime has attached to it a copy of the infinite space of possible jets. One jet for every way phi could locally behave there. The base space, the ground, is spacetime itself. Above each point rises an invisible tower, containing all possible combinations of derivative values. The whole collection of these towers across all points is the jet bundle. A particular physical field phi does not occupy every possible jet in every tower. Instead, at each point, it selects exactly one jet, the one that matches its actual derivatives there. If you could paint those chosen jets in each tower and ignore the rest, you would see a thin thread running through the whole jet bundle, a specific path in this vast space. That path is the actual state of the universe, expressed in the language of jets. The physical laws, our constraint chains, define which paths are allowed. They carve out a special subregion of the jet bundle, a smaller tree within the bigger forest, and say, only paths that run through this region are permitted. Once you see this picture, many familiar things in physics become easier to understand. When a theory is mathematically well posed, it means that the constraint chain defines a consistent subregion of the jet bundle, and that, given a suitable starting jet, there is a unique path that flows from it. When a theory breaks down at a singularity, it means that the path has run into a place where the required jet cannot exist with finite values. When we talk about renormalization or effective field theories, we are really talking about which parts of the jet we pay attention to at a given scale and which higher derivatives we average over or ignore. This mathematical coherence also has a direct linguistic analog. The jet bundle is like an infinite dictionary attached to every point in spacetime. It lists every possible local word the field could speak there. The constraint chains are the grammar rules that tell you which sequences of words are allowed in a sentence. A physically possible history of the universe is a grammatical sentence, a sequence of locally allowed words that obeys all the rules of agreement and order. An impossible history, one that breaks the laws of physics, would be like a string of random syllables that no native speaker recognizes as language. The point of the Holophase program is that we are not inventing this language. We are carefully listening to how reality already speaks and translating it into this structured framework. Seeing Holophase in terms of jet bundles also clarifies the role of the triunity of time, space, and motion. The jet at a point always includes derivatives with respect to time, derivatives with respect to spatial coordinates, and mixed derivatives that mix time and space. None of these can be discarded. They are all part of the jet's identity. When we talk about temporal echoes, spatial echoes, and motion echoes, we are simply organizing the entries of the jet into three families according to which directions they differentiate along. The deep symmetry that mixed derivatives commute is exactly the statement that these families are tightly interwoven and that time and space are not separate shelves, but different ways of asking about the same underlying field. This brings us to the question of falsifiability. A mathematically coherent framework still has to match reality. The Holophase picture claims that any physical system we encounter can, in principle, be expressed as a phi field whose jets obey certain constraint chains. This gives a clear way to test the framework. For any system that we can measure in detail, we can try to identify a plausible phi, construct the relevant constraint chain, and compute the jets and their echoes. These predictions then have to agree with what we see when we look at the system in time, in space, and in motion. If they do, the holophase mapping is supported. If they do not, we have found a place where the mapping is wrong, either because we chose the wrong phi, the wrong constraint chain, or because the entire idea of describing the system as a smooth jet of a single field fails. In practice, the remarkable success of differential equations throughout physics is a long, slow confirmation that describing reality with fields and their derivatives is the right kind of move. From planetary orbits to electrical circuits, from fluid flows to quantum energy levels, the same basic structure repeats. We write down a field, we write down a constraint on its derivatives, and we find that the solutions describe the world more and more precisely. The Holophase program does not replace this tradition. It extends it into a single unified story where all these different fields and laws are seen as manifestations of one underlying derivative language. You can already begin to see signs of mathematical coherence in simple everyday phenomena. When you watch a pendulum swing back and forth with a steady rhythm, you are seeing a system that follows a smooth path in its jet bundle. The angle, the angular velocity, and the angular acceleration all fit together in a simple harmonic relation. When you watch smoke rising from a candle and then suddenly turning turbulent, you are seeing a system whose jets at first sit in a calm region of the constraint chain and then move into a region where tiny changes in initial conditions explode into complex patterns, yet still obey the same underlying equations at every point. At the end of this bout, we return once more to phi itself. The mathematical structures we have described are not cages we are forcing onto reality. They are maps of the coherence that reality already displays. Phi is not a random, jagged, discontinuous chaos. If it were, there would be no stable orbits, no conserved quantities, no repeating patterns, and no science. The fact that we can write down differential laws and that they work is evidence that phi behaves like a smooth field most of the time, that derivatives exist, that jets make sense, and that consistency conditions are satisfied. The holophase language is our way of honoring that coherence and making it explicit. As we look back on our climb, we can see how this mathematical part fits into the larger story. We began by discovering the holophase alphabet, then the dimensional echoes, then the three echo towers, then the interweaving and the infinity of the tree, and finally, the universality of the language. Now, with derivative closure, jet structure, and consistency, we have shown that all of this lives on top of a precise, internally consistent mathematical foundation. The master tree is not just a metaphor. It is a faithful picture of a jet bundle, populated by a single smooth field whose changes write the story of the universe. We close with a quiet reflection. The universe is not only beautiful, it is also logically coherent. Beneath the swirling complexity of waves, particles, and galaxies, there is an order in how things change, an order that can be captured by derivatives and woven into a consistent framework. The holophase invites us to see that order as a language, to see phi as a speaker, and to see ourselves as listeners slowly learning the grammar. Every experiment, every prediction, every successful equation is another line in that unfolding conversation. To make this even more tangible, let us walk slowly through a few concrete illustrations of these ideas. Imagine first a simple vibrating string on a musical instrument. The displacement of the string at each point in time is one choice of phi. The value of phi tells you how far the string is from its resting position. The first derivative with respect to time tells you the velocity of each point on the string, how fast it is moving up or down. The first derivatives with respect to space tell you the slope of the string, how sharply it bends between neighboring points. The second derivatives tell you how the curvature of the string changes and how the acceleration of each point behaves. All of these derivatives together form the jet of the string field at each point. The wave equation is the constraint chain that links these derivatives together. It insists that the second time derivative of phi is proportional to the second spatial derivative, making the string's motion a consistent sentence written in the language of jets. If this equation were violated, the string would do impossible things, like suddenly jumping into a new pattern without any cause. The fact that real strings obey the wave equation with extraordinary accuracy is one more piece of evidence that nature respects these grammatical rules. Consider also the weather above you. The air temperature, pressure, humidity, and wind velocity can all be treated as components of a combined phi. At every point in the atmosphere, the jet of this field contains the local gradients and curvatures of each quantity, both in space and in time. Weather models take these jets and apply constraint chains such as the Navier-Stokes equations and thermodynamic laws. The result is a prediction of how the jet will move through its jet bundle, how the whole pattern of air will evolve. When forecasts are accurate, it is because our chosen constraint chains align well with the actual constraints nature enforces on those jets. When forecasts fail, It tells us that our constraint chain is incomplete. Our numerical resolution is too coarse to capture important derivatives, or our initial jet estimate was inaccurate. In every case, the game is still the same. Reality chooses a path in the jet bundle, and we try to guess that path by understanding the rules that govern it. You can even see jet-like thinking in the movements of your own body. When you reach out your hand to pick up a cup, your brain is not calculating explicit derivatives in the way a mathematician does. Yet your nervous system is exquisitely sensitive to how positions, velocities, and accelerations relate. Your arm follows a smooth, coordinated trajectory because your muscles and neurons are implementing, in a biological form, a consistent constraint chain on the jets of your body's configuration. If the derivatives were wildly inconsistent, you would jerk, tremble, or miss the cup entirely. Neurological disorders that disrupt smooth motion are often, at root, disruptions in the nervous system's ability to maintain coherent relationships between these implicit derivatives. In that sense, even the simple act of reaching for a cup is a living demonstration of mathematical coherence. It is helpful to contrast this with a world that did not have such coherence. Imagine a universe where the equality of mixed partial derivatives did not hold, where the change of a quantity in time and then in space gave a different result from the change in space and then in time. In such a universe, the notion of a stable, continuous field would collapse. Local predictions would depend on the arbitrary choice of path in the space of directions. Physical law would no longer be expressible as neat differential equations because the jets would not obey the basic grammatical rules. Inhabitants of such a universe could not rely on consistent cause and effect because the same initial conditions could evolve differently depending on hidden path choices in the derivative space. The very idea of a scientific method would be deeply undermined. By contrast, our universe seems remarkably well behaved. Mixed derivatives commute to extraordinary precision in all regimes we can probe. And wherever they appear to fail, as in shocks or phase transitions, we can usually understand the breakdown as a boundary between two smooth regimes rather than a true violation of the rule. From this perspective, the Holophase framework is not an arbitrary philosophical overlay, but a description of the deep regularities that make science possible at all. Derivative closure means that explanations can be refined indefinitely, without changing their basic form. Jet structure means that local behavior can be captured by a finite, organized collection of derivative data, at least to any desired level of approximation. Consistency means that these local pieces can be stitched into global histories without contradiction. Together, they tell us that the universe is written in a language where questions about change always have compatible answers. You can ask how something changes in time, how that change varies in space, and how the resulting pattern moves, and you will not be forced into paradox. The same phi underlies all of these perspectives. This also suggests a more personal way of relating to the mathematics. Whenever you sense that the world is intelligible, that your efforts to understand it are not in vain, you are feeling the presence of this coherence. The fact that you can learn physics, that you can trust that an experiment performed today will give the same result tomorrow under the same conditions, is an expression of the same derivative grammar. Mathematical coherence is not just an abstract virtue. It is the quiet background that makes learning, engineering, and even daily life workable. The Holophase picture simply brings this background into the foreground and gives it a precise name. Finally, remember that mathematical coherence does not mean mathematical completeness. Our models are always limited. We choose a truncation of the jet, we select a particular constraint chain, and we ignore higher derivatives that we believe to be small. Sometimes that choice is wise and the predictions are excellent. Sometimes it is poor and the predictions fail. Coherence means that, in principle, there is a deeper level to which we can go by including more of the jet and refining our constraint chains. It assures us that increasing resolution will not suddenly destroy the basic language, but will instead give us a sharper and more detailed version of the same story. In this way, the holophase encourages both humility and confidence. Humility because we know we never hold the whole infinite jet, and confidence because we know that what we do hold belongs to a framework that can, in principle, always be extended without breaking itself. Peace be upon you.